This video is going to give you a quick overview of the conservation of mass for differential control volumes, and then following videos are going to give you examples of how it can be used. So just to remind you, the conservation of mass for a differential control volume is written like this. We have d rho dt plus d rho u dx plus d rho v dy plus d rho w dz, and all that has to equal 0. All this is saying is that the rate of change of the density plus the rate of change of rho u, which is like a mass flow rate per unit area, add those all up, you have to be 0. In other words, what goes in and what goes out is all captured by this term here. So, interestingly enough, this is the transient term, so there's two times where this is 0. The first one's the obvious, right? If it were steady, then this term would be 0 because we don't have any d by dt's. But what else is interesting is even if it's unsteady, if it's incompressible, then the density can't change, and so again, that term drops out. Further, if it's incompressible, all of the densities can be pulled out of these, and you'll notice that then because this is gone, these divide away, and you're left with an even simpler version of this. Oftentimes we'll only look at one or two terms at a time because it could be 2D, so you might get rid of one. But overall, what this is going to be used for is relating the velocity field and the density field for the flow so that we can do things like actually find velocity profiles, where the integral equations gave us the high-level picture of what's going in compared to what's going out, the kind of bulk external effects. These differential equations have the power to actually give us the details of the field inside our region of interest. So let's move on and do some examples, and you'll see exactly how this goes.